Representing equilibrium reactions with particle views and/or graphs is quite helpful in understanding Unit 7 in AP Chemistry on equilibrium, Topic 8, which is representations of equilibrium, but it'll also help us understand the Le Chatelier principle that's coming in 7.9. In this one page of notes, I'll do an example problem with a particle view and calculate the equilibrium constant for each of these two halogenation reactions and compare them. Second, in this one page of notes, I will be using graphs to sort of introduce the concept of Le Chatelier's principle and where an equilibrium is disturbed. All right, so let's get started on the first one, which is using a particle view. How do we find kind of an estimated K value, an equilibrium constant value, based off of that particle view? All right, so the first thing you're going to need to do is count your particles. So this is our reaction. These are our ethene molecules. And what we want to do is count those for each of these particle views. Then we have our halogen, which is going to be just called X, which will be this one. And in this one, it's these for bromine. And then we want to count how many we get for this, in this case, some kind of halogen addition where we put those halogens on the ethene molecule, turning it into a single bond. All right, so let's just get started by counting out each particle. So for this one, what we're going to do is have C2H4 and count the number of particles, which is 1, 2. And then for the halogen, in this case chlorine, we have also 1, 2 particles of that. And then for our, it's actually going to be called dichloroethane, we have 1, 2, 3, 4, 5, 6, 7, 8 of those. So you count 8 of those. And then what I'm going to do is just do kind of a K, a C or something maybe, or it could be a KP. In fact, let's just call it a K because we're doing just particle counts. So we'll just say it's a certain number. And for this, you'll have the 8 in the numerator, and then 2 and 2 in the denominator. So our K is kind of this approximate equal to 2. And in a previous video, I talked about how we have the products in the numerator, reactants in the denominator, and then raised to the power. But these are all going to be to 1s because they have a 1 in front of them in the balanced equation. All right, so that's kind of how we calculated the K value for that one. Now we just do this again for the addition of bromine instead. So we still will count the C2H4, which is the ethene molecule. And I'm just going to count them with you. So 1, 2, 3, 4. And then in this reaction, this is at equilibrium. Both of these have established equilibrium already. And then the bromine, if you count, they're 4. And then the C2H4Br2 dibromoethane, I think, will be, let's just count those together. So we have 1, 2, 3, 4, 5, 6 of those. I missed one at the bottom, but got 6 of those. So the K value for this one, in fact, what I'll do is I'll just call this the K for the Cl2. And this will be the K for the Br2. We'll have, again, 6 in the numerator, raised to the power of 1, and then 4 in the denominator. And if you check with your calculator, or put those numbers in, you should get 0.375 as an answer. So the whole question here was which of these, if they've reached equilibrium, and which of these particle views has a larger K value. You would say then that the answer to this would be that the K value for the chlorine would be greater than the K value or the equilibrium constant value for the bromine, just because of the way that the reaction proceeds, meaning that you have more particles of product in this one compared to reactant. So you would actually argue that, again, this is in a previous video, you would say that this one is what's called product favored. And then you would call this one reactant favored. And you can really see that in the particle view. All right, so that's the first way we might use particle views to sort of understand what an equilibrium is and how this reversible reaction has reached equilibrium. And again, you would just, if you have the values, this would be your final answer, is that the K value for chlorine is greater than for bromine, or the halogenation of bromine. All right, let's move on to a graph of this now. So let's say this has already reached equilibrium. So this is our reaction that has already had an equilibrium constant that has been established. And then something happens to it. We add more N2O4. So that is our reactant. So which one of these graphs would be the graph of that happening? And this is leading us up to Le Chatelier's principle in 7.9 in AP Chemistry. So this first one, it goes up in concentration and comes back down for the NO2. And then what this is saying is this then gradually increases, which is the N2O4. Or is it that the N2O4, the reaction also has a higher concentration and then goes back down, and then the NO2 starts to be formed? Or is it that the NO2 stays the same, the N2O4 goes up and then drops below where it originally started? So think about which graph you would say matches what the example prompt has said to you. Okay, so first off, it's not this one, and it's not this one, and it is this one. Okay, so B is the answer. Now, why is that the case? I'm just going to write a really simple description. So it's no, because in this case, the NO2 was increased. If you look at the graph, the concentration of in this case, that would have been our product up here. The nitrogen dioxide was increased in concentration. I'm just going to do brackets so I don't have to save the words here. And that's not what happened. So if the NO2 was increased, that's not what the prompt actually has said has happened. All right, and then the next one is just the opposite of that, is that yes, because the N2O4, so dinitrogen tetroxide, is increased, and the graph is showing that in concentration. And then I'm just going to kind of put this into words. So if we increase this one, it'll go back down a little bit, and then we'll produce some product in the process of it. So because this is an equilibrium, we'll talk about it basically creating a Q value that will shift it to the right. It'll go down, not below where it originally started, and then the product will sort of increase. So it also matches that the NO2 will increase in concentration to adjust for that change that happened. And this will be a Le Chatelier principle that's coming into 7.9. All right, then this one's no, almost for two reasons. The N2, two things. The N2O4 cannot go below its initial concentration. So initial concentration, let's do brackets. And the NO2 sort of must change, in this case, to adjust for that. It's called a disturbance in the equilibrium. All right, so hopefully these two ways to represent equilibrium reactions have helped you. Again, first one was using a particle view and calculating the K value, the equilibrium constant, based off of just some general particles that we can count. And then the second was using a graph and kind of leading us into this topic of the disturbance of an equilibrium, which is the Le Chatelier principle.